All right, stationary points. We've already talked about stationary points. That is where you have a tangent being horizontal. So we're going to classify some things today, look at some more definitions. We know two stationary points. We're going to get introduced to a third one called a stationary point of inflection. Stationary point of inflection happens in an x-cubed graph. So off to the right there, I've got an x-cubed graph. An x-cubed graph has a tangent. That red line there is the tangent when x equals 0 is completely flat, but it's not a maximum and it's not a minimum. So what happens in the x-cubed graph, or any time when you graphed any polynomial graph in grade 12 that had a bend, that bend flattens out completely for a millisecond, or even less than a millisecond. Just for one instantaneous moment, it's completely flat, and that is a stationary point of inflection. It is the time where your tangent line actually cuts through your graph instead of just touching it and bouncing off of it. That is another type of stationary point. So we have the common ones, a maximum and a minimum, where if you drew a tangent, it would be flat. We also have stationary points of inflection, and we will find out that it's called a stationary point of inflection. We'll define inflection points later. Inflection points are where your graph changes how its curve goes. So on an x-cubed graph, part of your graph is curved down, part of your graph is curved up, and it's this point where it changes its curve from being concave down. We call any part of a graph that's curved like that concave down, and any part of a graph like this is called concave up. And an inflection point is where your graph changes from concave up to concave down, or vice versa. We have relative extremes, or local extremes, and absolute extremes. So sometimes we'll talk about a local minimum or a local maximum, and sometimes we'll talk about absolute maximums or absolute minimums. There is another picture of our stationary point of inflection. Okay. First derivative test. This is what we were doing earlier. We're looking at what happens when you find your stationary point, you find your critical numbers. Remember, critical numbers are where your derivative is equal to 0 or where you have non-permissible values. And if your derivative is positive before a critical number, and then your derivative is negative after your critical number, you would have a local maximum. And you can see that from your sign diagram. If it's your function's increasing and then decreasing, the only thing that makes sense is at that point you would have a maximum. Similarly, if your derivative changes from negative to positive, plugging a number into your derivative, if you get a negative, that means your function is decreasing. And then afterwards, plugging in a value, if you get a positive value in your derivative, that means your function changes to increasing, then you would have a local minimum. Randy. Whoops. I'm trying to find out where's. There we go. Yes, okay. So what we have happening here is whenever your function changes from an increasing function to a decreasing function, so if my normal function was increasing and then decreases, wherever that point is will be a maximum. And In this section, your derivatives will be positive. In this section, any tangent that I draw on this section will be negative. So that shows up on our sine diagram as we have a single point here. This part, your derivative would be positive, telling your function is increasing. This part, your derivative would be negative, telling your function is decreasing. And a minimum would be exactly the opposite. So if you had a function that had a minimum right here, it is decreasing before and increasing after. You would have that critical value from your derivative. You would find all the slopes before that point would be negative, telling you your function is decreasing. And you would find all the slopes of your tangent after that point to be positive, telling you that your function is increasing. So we call this the first derivative test, where you find your first derivative, set it equal to 0 to find your critical points, check where your function's increasing and decreasing, and then you can use that to tell whether things are maximums or minimums, or we'll find out, we can also use it to tell if we have stationary points of inflection. So we're going to find the stationary point of the function and show that it's a maximum using the first derivative test. So we already know that if we do have this as a parabola, it's a parabola that's opening down, we can already visualize that it's going to have a maximum. But using the first derivative test, what we would say is, I find my derivative, I set my derivative equal to 0, and I find a critical point at 5 over 2. Or, am I okay? All right. And then, what we have is, since that's our critical value, we have no non-permissible values. We can put that value, 5 over 2 or 2.5, on a number line, and we can check what happens when I plug in something less than 5 over 2 into my derivative. Anything less than 5 over 2 into my derivative, like -3, this will be positive, which tells us that our original function was increasing before 5 over 2. And anything after 5 over 2, you plug in 10 or 20 or whatever you'd like, will be negative, telling you that your function is decreasing after. So we can say as a statement, 5 over 2, comma, now if I want to find out what the value of my vertex is going to be, this is a point on my graph. I'm going to plug the 5 over 2 back into my original function. So I'm going to get -25 over 4 plus 5 over 2, which will give me 25 over 4, minus 28 over 4, -3/4. Ooh, that was a little bit too quick. Probably made a mistake. You trust me that I made a mistake? Thanks. Yes, but there's a negative out in front. You'd square this first, and then make it negative. -25 over 4 plus 25 over 2, 25 over 4, minus 28 over 4, -3/4. I think that's right. We're going to just, yeah? Okay. And what we can say now is a statement, 5 over 2 comma -3/4 is a local, it's actually an absolute maximum, but the first derivative test, I'll put that in brackets. Because f of x is increasing before x equals 5 over 2 and decreasing after. So the fact that our function is increasing before, decreasing after, tells us that that is a local maximum. In this case, it's an absolute maximum because it's a parabola going down. But that's how we use our first derivative test to show us. Our first derivative test is looking at how it's increasing and decreasing using our, and I'll call this a sign diagram where we label our critical point and check is the derivative positive or negative in each of the sections to figure out how our function is increasing and decreasing. Here's one for you to try. Found the critical point to be 2. So we find our derivative, set it equal to 0. Plug in 2 back into our original equation to get 2 comma negative 3. So, yeah, you could like I use the derivatives here. If you said since the function is decreasing before and increasing after, that would be fine as well. Yes. There we go. You figure it out that it's decreasing. So first of all, you know that this is a parabola, and that's why we start with examples like this. And when we say something is decreasing, it's going from left to right. And so this function is decreasing until we get to our vertex here at 2, negative 3, and then increasing after. So your y values are decreasing, and then your y values are increasing. Yes. And the derivatives tell us that because anytime I draw a tangent, any point here, I'll always get a negative slope. So whenever your function is decreasing, your tangent will always end up having a negative slope. Perfect. Okay. Your calculator, your graphing calculator, lets you find maximums and mins as well. So sometimes you can type a function into your calculator and use it as a way to check to see if you've got the same values that you did with calculus. And now we'll look at our stationary points of inflection. What is it going to show up when we have a stationary point of inflection? Well, you're still going to get a critical point. Your derivative is still going to equal 0. However, when you make your sign diagram, the gradient of the curve, your tangents will be either positive on both sides like they are in the x cubed graph. This function's always increasing or always decreasing. And so you've got a critical value, but in your sign diagram it shows that your function stays increasing. The only way that can happen is if you have a stationary point of inflection. Yes?
The stationary points only exist when you have 2 signs that are exact. 2 signs that are exact.
On your sign diagram, it won't change. Because if it changed, you would have a maximum or a minimum.
So if you set the derivative equal to 0, we get 0.
Yeah.
And then you
You do the line thing and you'd find out it's positive. Like, well, how simple is it to do x cubed, right? Here's x cubed. The derivative, 3x squared. It's equal to 0 when x is equal to 0. So then you get that value. When you plug anything into 3x squared, doesn't matter. It's going to be positive. So you're going to get positive whether you plug in a negative number or positive when you plug in a positive number. And so it's always increasing. And that's how we would know that there's a stationary point of inflection.
True for any like power or any odd function.
It's going to be true for any odd function. And we will see that it's true for any function that has a bend in it. And those bends don't necessarily have to be on the x-axis like we've had before. So we're going to see what that looks like. Anytime you have a stationary point of inflection, you're also going to have that your second derivative is equal to 0 at that point. So let's sketch a few graphs. Whoa, I didn't want to show you that one. I'm going to go to the other. There we go. Let's do this one together. X cubed plus 3x squared plus 1. So it's an x cubed graph, which might make us think maybe this has a stationary point of inflection, but maybe it has maximums and minimums as well. So starting off this, there's our first derivative. Set our derivative equal to 0. And solve. Well, we can factor out a 3x here, giving us two critical points. We have no non-permissible values, so the only thing we have to put on our number line is -2 and 0. Again, when testing whether things are positive or negative with your first derivative test, with your sign diagram, I like using my factored form of my equation. So I'll rewrite it here. Y prime equals 3x, x plus 2. And the reason I like using the factored form is because if I try something less than -2, like a -5, all I have to think about is my first factor is negative when x is -5. My second factor would be negative when x is -5. And a negative times a negative number will make this section positive, telling me my graph is increasing. Between -2 and 0, if I picked -1, this first factor would still be negative, but my second factor would now be positive. And a negative times a positive tells me that that part is decreasing. And after 0, if I plug in 5, 3 times 5, that'll be a positive number. 5 plus 2, that'll be a positive number. This will be increasing. So what that tells us is that we have two stationary points, and we can classify them. We have one stationary point at -2 comma something, our other stationary point at 0 comma something. We plug our values back into our original equation. -8 plus 12 is 4, plus 1 is 5. And 0 plugged in will be 1. We know that -2, 5 will be a local max because our function is increasing before x equals 2 and decreasing after x equals 2. We know that 0 comma 1 is a local min because it's decreasing before x equals 0 and increasing after x equals 0. If we go to sketch this, we've got -2 comma 5, zero comma 1, and our graph is increasing, decreasing, and increasing. And we've got a really quite accurate sketch of our graph. We know what its maximum is, we know what its minimum. This one has no stationary points of inflection. Okay? Oh, just looking back at this last one, a few things that you would have known from grade 12. From graphing polynomials in grade 12, what you would have had from this one is you would know, since it's an x cubed graph, a positive x cubed graph, you know its end behavior would have started down there and ended up there. You can't factor this. So there's no way that you could have found any x-intercepts. And that was how you sketched your graphs in grade 12. So the best you could have done is just a whole bunch of table of values and got a whole bunch of points in the middle and hoped that your graph was somewhat accurate. But now that we've got our calculus, by having our max and our mins and just drawing a nice smooth curve through it, we've got a very accurate graph with a very little amount of work. So our second one here, what would you have known from grade 12? Well, maybe I'll do that at the end. Let's do calculus first. Yeah, it's end behavior. Let's just talk. We know that it's end behavior like this because it's going to be like a parabola. Might have some stuff in between. Okay? So I'll compare what you would have been able to do in grade 12 with this graph compared to what we can do now. So here's our derivative. F prime of x equals 4x cubed minus 12x squared. Set that equal to 0. You can factor out a 4x squared, leaving you with x minus 3. And we have two values, two critical points, no non-permissible values. Set up our sign diagram. Again, I'm going to check things by plugging it into the factored form of my derivative when I plug in a negative number. First of all, can you see that this part of my factored form will always be positive 4x squared? So when I plug in a negative number, like negative 5, this will be negative. So that tells us this part is decreasing. When I plug in a number between 0 and 3, like 1, this is positive. 1 minus 3 is still negative. It's still decreasing. And then finally, choosing a number larger than 3, that will change this part to positive, which will be increasing again. If we check our values, so we have 0 comma something and 3 comma something. I plug in 0 into my function, I'm going to get 0 comma 0. I plug in 3 into my function, and I get 81 minus 108, negative 27. Yes? Okay, this one is going to be stationary point of inflection, and this one is going to be a local min, a minimum. Might be an absolute minimum, we'll see. When we go to sketch this graph, we can label our points. We've got 0, 0. Three comma negative 27. We know that our function is decreasing. We would have to have an inflection point, so there has to be a bend there. My scale is actually a little bit bad here. Just because I'm cheating a little bit, I'm going to make my scale better. There we go. So there's our graph. And how does this compare to what we had from pre-calculus last year? From pre-calculus last year, This one you could do more with. You know the end behavior, we talked about that already. You could factor this to begin with. In fact, you could factor out an x cubed, leaving you with x minus 4. And so some important things you would have learned from last year is you could have said there's an x-intercept at x equals 0 and another x-intercept at x equals 4. So we'll want to use that skill of factoring originally to find our x-intercepts. And from last year, you would have known since the x cubed has a multiplicity of 3, there was a bend at x equals 0. Does that? You don't remember calling them?
I knew what they were, but I just didn't know it was called multiplicity.
And because the 4 has a multiplicity of 1, this factor only occurs once, then your graph went straight through. And so we had things in place that allowed us to account for the bend in the graph and going straight through. But what we didn't have last year was how to find where that minimum would be. So combining the two, we find our x-intercepts, we'll find our y-intercepts, those will be important points to have, but now we can find maximums and minimums, and we have a better graph than what we graphed before. All right, so we are going to take some time to practice some of these.